Swayam Prabha. Digital India. Educated India.
Okay, yesterday we were talking about the inertial subrange of 3D turbulence, and we figured out that there were two constants, one appearing in the definition of the dissipation, another appearing in the microscale, and these two are not independent. This lower case of C k can be obtained in terms of the uppercase C k. So, this is one thing that we noticed. Now, one more aspect that you would like to note is that the kinetic energy, specific kinetic energy is given in terms of the energy spectrum here, and that you integrate from the largest scale to the Kolmogorov scale gives you this, right. If I put E of k as that k to the power minus 5/3 law, this is what we are going to get. So, that gives you an estimate that U goes as the dissipation rate times the outer scale raised to the power 1/3. So, if that being the case, then we can see the Reynolds number can be defined like this. Okay. Now, we have already seen the definition of the Kolmogorov scale like this. Okay. So, what I propose to do is that instead of epsilon here, I take the epsilon from this expression, right, nu r e by L to the power 4/3 is this, plug it in there, then you will see that lambda k goes as L times r e to the power minus 3/4. So, that basically is a very important information. What it tells you that if you are looking at the simulation of a, let us say 3D turbulence, then in the each direction the smallest relevant physical length scale as given by the Kolmogorov scale goes as r e to the power 3/4. So, that is lambda. So, if I now convert it in terms of the corresponding k, that will go as r e to the power 3/4, inverse of that. So, if I look at it that way, then what I find that the cutoff wave number that we are talking about, non-dimensionalized, scale says r e to the power 3/4. So, if you are doing a 3D flow simulation, so you will have a k c in the x direction, k c in the y and z direction. So, the smallest scale, the cube, would be given as the product of these three cases, right. That would go as r e to the power 9/4. So, that is what you would hear quite often, that if you are trying to simulate 3D turbulence, the number of points required in DNS goes as r e square. So, that is r e 9/4 is close to r e square. So, it is a kind of a simplification. So, this is something that you should know, that if you have done a simulation for some Reynolds number, you double the Reynolds number, your requirement on the number of points would go r e to the power square. So, it will be squared, right. So, this is something that we need to remember. Now, people do also talk about another scale, which is called the Taylor microscale, very popular with the experimentalist. They basically try to find out some kind of a integral scale and the RMS velocity fluctuation. What you do is with the help of this, you define a Reynolds number based on Taylor microscale, which is that V RMS times that Taylor length scale divided by nu. So, what happens is then we can go through this as the V RMS goes as velocity scale itself, and if I am looking at, let us say, one of the component of the velocity, then what happens is this quantity, the velocity gradient, would scale as the velocity scale square by lambda square. So, that there is another way of defining the Taylor microscale, that gives you a kind of a curvature of the velocity autocorrelation, or you could look at it as a width of the energy spectrum, right. That is what we are doing. So, I am doing it k square E k d k divided by this, and what this we have seen already. This is nothing but the velocity gradient scale, and this is nothing but the velocity scale, and this also we have seen is proportional to entropy. So, this inverse of the Taylor microscale squared is a ratio between the entropy norm by the velocity norm. So, this is something that experimentalists do talk about, and since we have these estimates of the velocity scale going as dissipation rate times outer scale raised to the power 1/3. So, we can use that and plug it in, and this is what we get. So, what happens is the Taylor microscale actually goes as r e to the power minus 1/2. So, basic idea is for you to know that from a different perspective, depending on the Reynolds number, you may require to sort of resolve some of those scales, right. So, if we are, let us say, for example, looking at homogeneous isotropic turbulence, then we can talk about the Kolmogorov scale, Taylor microscale. They all go as r e to the power minus 3/4 and r e to the power minus 1/2 respectively. For inhomogeneous non-isotropic flows, we can still talk of the Kolmogorov scale, although we have not seen any such definitive proof of it analytically. However, we can see this lambda, the Taylor microscale, actually depends on the Reynolds number itself. In addition, you may like to resolve various other length and velocity or time scales. For example, if you are looking at boundary layer itself, the boundary layer thickness is proportional to r e to the power minus 1/2. So, that is like your Taylor microscale, right. So, you can understand that that could be also important, even though you are not looking at turbulent flow. If you are simply looking at perturbed laminar flow, you should be able to resolve those kind of scales. Okay, so, let me now go and spend a little time on 2D turbulence. 2D turbulence, as we can think of, that it does not have vortex stretching mechanism. So, we do not have an energy cascade, that nonlinear term is missing. If we look at unforced inviscid 2-dimensional flows, then what we can see is that energy and entropy are both conserved. That comes out from, let us say, writing down the equation, the vorticity transport equation for 2D turbulence in this form. So, what we have done, we have taken the vorticity transport equation in 2D, multiplied by omega and integrated over the whole domain. Then this is the total rate of change of entropy, that is given in terms of the entropy dissipation rate, right. So, this is nu times gradient of omega. See, in 3D turbulence, this was omega square itself, but it is now gradient of omega square. So, this is something what we call as the entropy dissipation rate, symbolically written by this by chi, and you can plug it all the values. Omega itself has a dimension of time, 1 over time. This is gradient operator is 1 over length scale. Nu has a dimension of L square by T. So, plug it in, you will find that dimensionally this entropy dissipation rate has a dimension of T to the power minus 3. Okay. Now, if we are looking at unforced 2D flow, then what will happen? If it is inviscid, then this term is not there, and if the body force is conservative, this term is also not there. So, this basically says ddt of the entropy is equal to 0. So, that is what we are saying. For 2D flow, what you find that you have two requirements, both energy and entropy are conserved. In 3D, what we saw, energy was conserved, but entropy was increasing because of vortex stretching. Now, if per se in a flow we have these quantities as constant, then by some mechanism energy is transferred from a larger scale to small scale. That is what we call as the forward scatter or the cascade. Okay? So, energy is going from large scale to smaller scale. Then because these two have to be conserved, then we must also have a reverse migration, so that these two integrals remains conserved. And this complementary phenomena where energy transports from smaller scale to larger scale is called the inverse scatter or back scatter. In 80s and 90s, there were lots of results related to the back scatter. You can think of it in the following sense. What was the forward scatter? Forward scatter were larger eddies breaking up into smaller eddies. So, back scatter is just the reverse, smaller eddies coalescing and forming bigger eddies. And this is one of the aspect of 2D turbulent flows. Okay? So, this is something we must keep in mind. Now, well, let me now show you something else which I will let me just show you something else. This is the story for 3D turbulence, right. That is the way the energy cascades k to the power minus 5/3, and this is your corresponding dissipation spectrum for 3D flows. What happens to 2D flow? We have not talked about it, right. So, if I want to talk about it, then what am I going to get? What am I going to get is what I have written here. Like if I have a 2D turbulent flow, then once again I have some energy coming in and then energy has to be drained out, like what we see here. And here we are talking about instead of energy, we are talking about entropy. Why? Because in 2D flow energy was conserved. For 3D flow energy was conserved, and that was our consideration in getting the inertial subrange. But in this case for 2D turbulence, if we look at inviscid flow, then what happens? This itself is conserved. So, whatever the role that was played by energy in 3D flow will be played by entropy in 2D flow. That is why there when we talked about an inertial subrange, we wrote the energy spectrum to be dependent upon energy dissipation rate and the wave number. Here for 2D turbulence, then I will be talking about this energy spectrum to be dependent on entropy dissipation rate times and the wave number. And we have already seen yesterday, this is the dimension of energy L cube t to the power minus 2, chi we have just now seen here, it is t to the power minus 3. This is of course 1 over L. Do a dimensional analysis and you find this. This is something rather interesting, that if you compare it with 3D flow, here the energy spectrum dependence for 2D turbulence is given by k to the power minus 3. So, I am not doing it, but I am suggesting to you to tell me what happens to the dissipation spectrum then in this range. This is something interesting. This is completely different than what we have talked about for 3D flows. 3D flows we saw in the previous slide that dissipation spectrum was going up like k to the power 1/3. Here it will come down as 1 over k. A very interesting thing. So, the requirement of a 2D DNS versus 3D DNS are not necessarily the same. We should keep that in mind. Now, Are this somewhat real or not is something that we need to understand, but having seen the difference between the 2D and 3D dissipation spectrum, we need to really understand what we do when we actually numerically solve. This is a picture that tells you about how you discretize the dissipation term by various methods. So, if I take a let us say a second order central difference scheme at higher k, I actually have a significant loss. It is about 0.4. So, 60% loss of dissipation. This is your CD4. Then this is one of that high accuracy scheme, compact scheme proposed by Lele, and this is what we often used, which is called a combined compact difference scheme. We have been doing it for quite some time, and the last figure is interesting. Last figure is that you use high accuracy scheme for first derivative twice to get it. It is interesting in the sense that when you look at this property, that it remains faithful all the way up to 2 and more, and then it falls off to 0, right. Whereas in CCD you will see always that high wave number is overestimated, and we have seen, those of you who have some exposure in computing, you know that aliasing is a major source. So, if you want to knock off, remove the bad adverse effect of aliasing, this kind of overestimation of dissipation is not bad. In fact, that might turn out to be very positive. Now, let me just simply close here on a note of what do we actually see in nature. This is a power spectral density for atmosphere. What you are seeing is basically the zonal wind, the meridional wind, and the temperature field. Well, this is along the longitude, along the latitude, and this is the temperature distribution. It is plotted versus wavelength. Also in the same scale, if you read from the other side, you will also get the wave number. So, this is what you are seeing. So, what you are noticing, a very interesting thing, that this is of the order of the planetary scale, you know, the sort of the periphery, the 2 pi d of Earth in that range, tens of thousands of kilometer, and here these are in kilometer, this is 10 to the power minus 2, minus 3, etc. What you are seeing is the first part, the dependence is like k to the power minus 3. Okay. So, in the large scale in atmosphere, you do see attributes of 2D turbulence. So, this is not something that is just simply academic, we do see that. In fact, what you see that this 2D turbulent feature is followed by 3D turbulence feature. This is your minus 5/3 slope. Okay. They have been shifted laterally for viewing. So, otherwise there is it would look cluttered if it were all put one over the other. So, basically I think on this note I would stop saying that do not keep your mind closed, because you can see, as the greatest fluid dynamical lab could be, your atmosphere shows the presence of 2D turbulence. So, people tend to overemphasize on vortex stretching 3D turbulence, but 2D turbulence is equally relevant, and this is direct evidence. This was given in this reference by Nastrom and Gage, published in a Journal of Atmospheric Science in 1986. They actually employed a fully instrumented aircraft and made it fly around the globe. That is how you could sort of get the whole scale. Okay. So, there you have it. So, I think on this note I will just stop it, and let us have a discussion of whatever we have gone through the whole semester. So, this is your time. to really have this meaningful discussion, and let's go ahead and do it. Okay, let's get started. So you all completely comfortable? No questions? You get started if you wish to. If you want, you can take the.
Sir, I would like to ask about the difference between the excitation with acoustic waves. Like it doesn't trigger the TS stabilities. Like what is the basic difference?
Well, the acoustics can create. It has the receptivity, but the mechanism is little more subtle than, let's say, the vibrating ribbon experiment of Schubaur-Scramstad. They originally started with the excitation, acoustic excitation to generate TS wave. They were not successful, simply for the reason was the calculations were for 2D Tolman-Schlitt string waves. So, you have to create a disturbance field that is 2 dimensional. Can you create a 2D acoustic wave? So, you see this is also we touched upon when we talked about Klebanov mode. Why Taylor could not detect TS wave? Because he was using a mechanical vibration all right, like the vibrating ribbon, but his frequency did not match. So, it is very, very important. I mean, if you are trying to compare your theoretical result with experimental result, you must compare apples with apples, not apples with oranges, right. But if you do have acoustic excitation, like we did some calculations few years ago for supersonic flow, you can create disturbance waves, but it may not work out like TS wave. There we saw it is more like a bypass event.
Sir, for the mixed convection problem, how do we exactly arrive at flow assisting and non-assisting flow? I mean, with the sign of K.
Well, with the help of your direction of the gravity, see there the body force was due to the buoyancy term. That's your Boussinesq approximation. So, if the gravity assist the convection, how the convection would go from a hot to a it will rise up, isn't it? If we are looking at on the top side of a plate, if I look at the natural tendency, lighter fluid will rise up. So, that is the direction. So, if your buoyancy is also in that direction, then of course, it is assisting. But if you look at the bottom side of the plate and if the plate is still hot, then what will happen? Then it will be opposing flow, right. So, that is the way to interpret it.
So, in the case of laminar flows, you are saying that the energy spectrum contains peaks of particular points. Do they correspond to the vortex, the largest vortex sizes?
So, if I let us say look at the wake of a cylinder, as a very canonical example of what we see. How will we see? If I plot E of k, you may just simply see sufficient energy at the means 0 k means the largest possible scale that you have, and then it may just simply have this, and then corresponding to a Strual number you will get this. And of course, it is a dynamical system, nonlinear dynamical system. So, if I excite the system is susceptible to that frequency, it will also be susceptible to its superharmonic, subharmonic. So, you do get that, and we did not talk about, but if you let us say take a cylinder and start doing this rotary oscillation, right, then you can really see the presence of various sub and superharmonics. So, you will see that kind of a picture like this and something like this, and that is it. Whereas, if you look at turbulent flow, but now we have seen that it is a wide band phenomenon. So, energy resides over a large range of. You have any questions? Satyanarayan?
Are they Blasius point of inflection and stagnation?
Pardon?
Blasius point of inflection from there.
No. Let us try to get the question clear. You are saying if you have a stagnation point flow, that is not called the Blasius flow, that is called the Hemans flow. Okay? So, what is the question? If the stagnation point is a point of inflection or not? See, the thing is, if you also look at the Blasius profile, what is the value of the second derivative of the velocity at the wall? It is a 0 pressure gradient. So, second derivative is related to the pressure gradient. So, if I take a 0 pressure gradient flow, the second derivative is 0 on the surface, but that is not a inflection point, because inflection point is across which the slope changes sign, but you do not have anything across, you stop there. So, that condition that we have talked about, you probably are hinting at Rayleigh's condition, right, Fjortoft's condition, that you have to have an inflection point to be invisibly unstable. But if you have it right on the surface, it does not cause a problem. But if you have it off the surface, if you have an inflection point, then you would get violent instability. In fact, for any velocity profile which displays inflection point, they are going to be very violently unstable. For example, if you look at say jet or mixing layer, the critical Reynolds numbers are less than 100 even, something like 3, 4, in that range you can find those flows to be. Well, the question is at those Reynolds number whether it is right to consider the flow to be parallel or not, it is a different issue altogether. Okay. So, any other questions? Anybody having any particular question to Piyush?
Sir, we discussed about Kolmogorov scale. So, when we do computing, these scales are affected by computing.
The scales of course is not affected by computing, but your computing should be able to resolve those scales. That is what we made the point, that Kolmogorov scale is the smallest scale that is excited in a flow. Beyond that, everything is dissipated into heat. So, you cannot have eddies smaller than that size. So, you cannot have fluid flow entities which will be retaining its identity and having a kinetic energy at that scale, beyond that scale. So, that is what you want to do in direct numerical simulation. When you are trying to solve the equation, you are trying to resolve all the way up to Kolmogorov scale.
Less than Kolmogorov.
Well, up to.
But then there are the restriction on group velocity, also the Q waves, so that also.
Well, we would what Shagato is raising a point is something more, that what we talk about, what do we exactly mean by resolution? Suppose I solve numerically and I have a resolution given by this grid spacing, right. So, what we know that this is your maximum resolved wave number. Theoretically speaking, this is the maximum that you can resolve. That is what you do if you let us say do Fourier spectral method. You take any other method, what will happen? You will not be able to exploit this whole thing. So, that is why he is saying that if the Kolmogorov scale is here, your method should be farther on this side, because you do not, if you are looking at say transfer function of the method, say if I am trying to let us say show the derivative, if I have to calculate this, one of the shear derivative, let me say that this what I am trying to do numerically divided by let us say the derivative which I have for exact condition, then Fourier spectral method gives you this kind of a picture. Any other method you get a part of the range, better the method you will get more and more. See, this was something that we saw. We saw here as far as the second derivative representation was concerned. Ideally, I would have liked it to be equal to 1 all the way, but different methods filter it in a different amount. So, he is saying that do not draw your conclusion based on this maximum limit, because your method starts deviating. For example, I said that if you look at this purple curve, I get only 2/3 of it resolved. So, his question is a very valid question, that I may not be able to resolve the derivative itself properly. Now, added to that is the main thing about this course is, are we faithfully reproducing the physical dispersion relation computationally or not? That comes about from the group velocity we have seen. And what we find that the physical group velocity and the numerical group velocity usually has mismatch over a large range of k delta x. So, this is all about resolving a derivative. That still does not give you the full picture. A better picture would be where you resolve this, you also satisfy the physical dispersion relation. This is what is called as a topic, which is common when people quote it, very also common in misunderstanding it. There are lots of people who can claim, who do claim that they have method which preserves so they call it DRP schemes. So, they say that we have developed numerical methods which preserve dispersion relation. But what one should do actually is look at what your numerical method is doing, what is that method's dispersion relation is the numerical dispersion relation, compare it with physical, you have a very small intersection. So, talking about this, if I am happy with this method, my dispersion relation may actually bring it down further. So, what we are saying that DNS as it is practiced by many people across the world, they have serious limitations. They do not even understand what is really a DNS ought to be. If you do not understand your numerical dispersion relation, you have no way of knowing what you are doing. Unfortunately, that is the state. But it is good that Shagato pointed this issue. What I was doing, I was parroting what everybody says, that the lowest common denominator is at least you should be able to resolve this. If your numerical resolution itself is here, then you are not even going up to the Kolmogorov scale. That is a lost case anyway. So, there are various other issues. For example, we have not talked about another source of error that comes about because of aliasing. That is also in nonlinear or product terms. That is where evaluating this product terms you associate aliasing. So, that also limits your resolving ability significantly. There are lots of such issues. Those of you, well, my point of view in this course is that of course, we learned quite a bit about theoretical results related to transition and instabilities. If we want to compute them per se ab initio without making an assumption, then this sort of issues come into picture. We have to really take care of it. And the good news is the ability of high accuracy computing is increasing so dramatically that we are now in a situation where we can talk about nonlinear flow instabilities being computed, and we have done one such thing. You have seen, we talked about proper orthogonal decomposition in this course. We did also relate those POD modes with the instability modes. This is a new subject in the horizon. I mean, it's being done here currently. We have explored a whole range of flows, starting from flow past a streamlined body, flow past blob bodies. We are seeing that if we could relate this POD modes with the instability modes, and we have come out with a point of view where we see some universal features appearing, like Rajarshi will tell you that if you compare a flow past a cylinder, its external flow, versus a flow inside a driven cavity, they may look completely different. But when you look at their POD modes, you will see those basic building blocks are identical. So, there are lots of exciting things happening. They are possible now. We are now in the threshold of talking about nonlinear instabilities in a full fledged way. I think the future looks absolutely bright, absolutely bright. There are lots and lots of things those are happening here in our lab. People are paying attention, and this is a very, very hopeful sign. But let me tell you, think of computing. Don't think of computing in isolation. You can be at the most a glorified clerk. You will be able to get some code and you can run it, but you have to understand the physics of the flow. And I hope this subject actually exposed you to some of the nuances of instabilities, turbulent flows. Without that, you wouldn't even know what you are computing, right? For example, we just are talking about dissipation, discretization. This may look good. That is what we understood. See, if I understand what the dissipation spectrum is, we know that is where it peaks up at the highest wave number. So, I cannot just simply say, oh, I am doing perfectly all right up to here, this side it should be. Lots of people talk about discussion on resolving scales only in terms of energy spectrum. But what you need to do is basically energy spectrum information should be supplemented with the dissipation spectrum, because you saw the whole idea of Kolmogorov spectrum and all relates to the balance, that whatever you are putting in, that is exactly going out, and if the dissipation is not modeled properly, you will go haywire, you will settle down to a wrong equilibrium condition. Okay. So, any other things? Well, I mean, if you have some question you can ask, otherwise we will just say good luck to you. Hope you will be continuing, some of you solving some of these problems, and come out with some new interesting finding. Some of the topics which I could not do, which I could have touched upon, but lack of time prevented, is the instabilities of three-dimensional flow, especially from the perspective of aerospace engineering. For example, if you look at flow over a aircraft wing, then you can have the flow going in one direction, disturbances may go in another direction. We talked about it when we are talking about spatial and temporal instabilities, and that is what you see, that the phase goes in one direction, growth is in another direction, mean flow is in the third direction. And what we actually do, currently the state of art is, of course, one way is to be able to do a complete DNS. It is not so trivially done. We are making some preliminary effort in that direction, but what people do theoretically, they isolate the problem, like if the disturbance were growing in the streamwise direction, then I get some instability criteria. If instability was going in the cross flow direction, then I get another criteria. So, we are just simply talking in terms of various criteria depending on if the disturbances were going preferentially in one particular direction, but actual flow it may not be so. So, there are lots of such things which I would have wanted to do, but lack of time prevented. But nonetheless, the basic mechanisms have been covered, and one of the distinctive aspect of this course would be emphasis on receptivity. We do believe, continue to believe, we have not seen anything contrary to our belief, is that all flows are excited. You cannot just simply talk about a flow past a sphere which is perfectly spherical in shape, flow is completely uniform, and then you get turbulence. It is not so. We got to understand what the background disturbance is doing to the dynamics. Like the dynamical system point of view is the main thing. We should look at the dynamical system. Instability study relates to the transfer function, but we also say the input is important to understand what we see in the output level, right. Otherwise, the picture remains incomplete. Okay, so I think we will close here. Thank you.